For those who have, I think, or you guys already download the lecture 3. You can go to the Google Classroom, and then you can open that slide. Okay. Bismillahirrahmanirrahim. So today, going to learn about CMOS transistor theory. Can you see my screen?
Yes, madam.
Okay, right. The CMOS transistor theory on the non-ideal effects. Okay. First of all, this capacitance we learn. We know that if we have still some people coming. Where is my pen? The pen. Okay, about capacitor. In order to have a capacitance, we know that any two conductors separated by insulator, we have capacitance. If you look at our if you look at our transistor, okay, kejap. Let me draw. Can we draw? Yes. Okay. This is the okay. This is the transistor N plus, the substrate, the P substrate. Sorry, but actually my pen, I changed my pen. Then this pen actually is not really accurate, and then it's not really giving a straight line. So this is a gate. Right. So this is in between gates and this thin layer here. This is an oxide layer. Okay. And we know that there's a supply here. And this oxide layer is actually the insulator. So between these two conductance, we can have the capacitor in between this. Sorry, I can, maybe you cannot see that. This is a capacitor for oxide layer, the C oxide. If I can draw a little bit bigger, this is a gate, this is a C oxide layer, and then the N plus here, and another N plus. Okay. And then there's another one, capacitor at this side. This is a gate, right? So this is a capacitor for, because this is a, the source and the drain over here. So this is source of the source to gate capacitance. Okay. So for gate to channel capacitor, this is a very important, which is the COS. It creates channel charge necessary for operation. And the source and drain have capacitance to the body here. Okay, because this is the P substrate, right? And another one over here, the C of the source and body, and also capacitance for drain, and also the body. Sorry, tak cantik. But we do not want this two capacitance. We want to eliminate as possible the capacitance, the parasitic capacitance in these transistors. Okay, so for this part, across the PN, we know that this is P sub with the N well here. They will have what we call it a reverse bias diode, right? Over here. Okay. And it is called diffusion capacitance because it is associated with the source drain diffusion. Okay. So for the MOS structure, it looks like a parallel plate. Like if you look at on your left side, this is a 3D. And from the previous class, Prof. Anis already explained, this is the width, right? And we have the length over here. This is a channel length. And then based on this transistor in 3D, we can have a cross section on the right side here. And if you look at this, this is more clearer. We have the capacitance at the gate or the in between this. So this is CG. And then like I said before, there's another capacitance of the drain and also the bulk. And the capacitance of source and bulk. Okay. So for the MOS structure, we have this one gate, and then outside layer, and then the channel, right? So charge, we know that charge is equal to capacitance into voltage, right? From our previous theory. So from this, capacitance can also be measured in terms of the area of the transistor. Where is the area? This is the area, the width into the length of your transistor into the this is the epsilon outside, and divide by the thickness of the outside, which is this layer, or simply said this part. Okay, and if you substitute the equation on your right side here into this equation, then you will get this one, right, into the area. So you can actually control the capacitance value by making this capacitance of the outside or this part lower, because we want to reduce the parasitic capacitance as possible. And then next, the voltage also can be found from the...
Okay, sekejap Dr. Arfa. So C gate is the capacitance between the gate and the channel, and this is important to isolate the gate and make sure that the current in the gate does not go to the channel. So they want a good insulator there. So here it is not a parasitic, but it is necessary. But the others are parasitic capacitance. Okay, Dr. Arfa, you can continue.
The CG is not the parasitic. Okay. The parasitic is actually at capacitance between this and between this. Right? Right. And then another one, okay, for the good insulator, usually we have this, if you use the silicon dioxide for the gate outside, the epsilon outside layer is equal to 3.9, this one. Okay. So for the gate capacitance, the approximate channel is connected to the source is equal to this. So this is the area into the epsilon of the outside layer divided by the thickness of this gate, the insulator side. And then what is the C per micron? What is the C per micron? It is a capacitance per micron, which means that you can partition the gate into smaller squares. That's why they put it per micron, which is maybe this is a per 1 micrometer, this one, right? Per 1 micrometer. So if the C per micron, capacitance per micron is equal to like about 2 femtofarad per micron, then if you have like a 10 micrometer, then you can just multiply the 10 into 2 femtofarad per micron, and you will get 20 femtofarad per micron. Okay. Okay. So your task is actually to minimize the diffusion capacitance, because we know that at this side over here in a normal condition, we have some depletion region here and then some depletion region here. And then if we supply something at the gate, then there's some channel will be built up over here. And if the gate is equal to 0, then our expected the transistor should be turned off. Over here there is no channel, okay? But if this is turned on, then the channel will be built up. But there's some condition when we know that there's a capacitance over here and here. The capacitance is actually the C of source to the bulb and capacitance of the drain to the bulb. And both is actually the parasitic capacitance. And this one, we want to eliminate or reduce this parasitic capacitance. Okay, so capacitance is actually, this parasitic capacitance depends on the area and perimeter. If you look at on your right side here, boleh tak zoom? Check. Okay, this one. There's 3 ways they put how to this one is actually the top view of the transistor you're going to see. The one you look at here, the black color here, the box like this is actually the contact of the 2 layers. Let's say you have one layer here and another layer here. You need a metal layer, a metal to contact these 2. Okay, so maybe this is a level 1 and another one is the level 2.
So that one is the cross section. So maybe you can explain a bit. The one you are drawing is the cross section, and that one is the top view. The one in the color. Okay, so this is what you guys are going to be drawing when you draw the layout design. So that is the top view. And the one Dr. Arfah is drawing right now is the cross section. And it's showing the layer between the metal at the top and the bottom layer. Okay, you can continue.
Yeah. So if you look at your left side here, the most left side, this is a source, right? And then drain, source, and drain.
Maybe you can explain one by one which one is which layer, because I think they're not familiar what is the pink layer, what is the green.
Okay. Betul. Right. The red color here is actually the gate. I better change the thickness. Okay. Okay, this is a gate, and this is also a gate. And then you have a diffusion layer, which is the green color here. This is also the diffusion layer. You still remember, right? Where is the diffusion layer? This here. This one. Okay. The diffusion pipe. So you have the gate. Gate is over here. And then the drain is this side. And then, no, the source is this side and the drain is on the right side. So if you, this is a 3D, but on the right side here is the cross section, right? So if you look at from the top view of this transistor, you will have something like this. So the gate is the red color, okay? And then you have the diffusion layer. And then on the down here, you have the source, and then this is a drain. So the source and drain should be contacted to the next layer, so that you will have the blue color here is actually the metal pipe, if I'm not mistaken, because usually blue for metal. So this is the metal contact. Metal contact, so that you will have some connection between layer 1 and layer 2. Whether this is a diffusion or to the gate. Okay, so so this is number 1, transistor number 1, and the second one is actually this one, transistor number 2. It has the same way. We have source here and drain the other side and gate in the middle. Right. So why we have 3 parts here? Actually, on the left side is the what we call it as an isolated diffusion. Why they call it isolated diffusion? Because of, if you look at the diffusion here, diffusion over here, it is with isolated source and drain. Okay, the diffusion have its own diffusion, isolate. In the middle, the B side here, this is called a shared contacted diffusion. So we know that the green color is actually the diffusion, right? This is a diffusion. So the contact here in the middle, over here, it is a sharing of these 2 diffusion. And if you look at on the C part here, it is a merge diffusion. Where is that diffusion? Diffusion is this one, the green color, and then it is actually merged in between the source and the drain. Okay, so why we have all this? Because if you look at our previous slide, we want to reduce the capacitance of the C drain to bulb, and also the capacitance of what we call here, capacitance of the source and bulb.
So you want to reduce the parasitic capacitance. You don't want to reduce the other capacitance, only the parasitic. So the parasitic is the unwanted capacitance. So we do not want them because they cause noise. So you have to look at where is the parasitic capacitance and you have to reduce it. And this parasitic capacitance can be reduced by making your layout. This is the layout. The green color and the red color guys are the layout. So you want to make it reduce. So as you can see, when you start from the left, it was 2 transistors. And slowly the layout, as you move to the right, the layout becomes smaller and smaller. So the rightmost layout is the optimized layout, or the one with the less area. When it has less area, it has less parasitic capacitance. Therefore, your circuit is optimized. Okay, everybody is okay? We will go through again. If you don't understand exactly which one is the drain, gate, source, It is okay. You just need to know where is the capacitance for this for now. Later we will go through where is the layout exactly, where is the drain gate source. All right. Okay, Dr. Alpha, you can continue.
So that's why if you look at this slide, it says that the parasitic capacitance depends on area and perimeter. So meaning that you need to design such that this diffusion is small as possible. This diffusion in between here, or diffusion at this side or this side. Okay, so make it small as possible so that parasitic capacitance also will be small. And then it is actually comparable to the gate capacitance for the contacted diffusion. And half of the gate capacitance for uncontacted, what we call it, this one is actually, all this depends on the process. Process of what? Process of the manufacturing technology. Okay. All right. And then we go to the short channel effect. Okay. For the short channel effects, the behavior of this short channel device mainly due to the one of it is actually the velocity saturation. But what
So
is
before that, maybe we explain what is the difference between long channel and short channel.
okay? So if we go back to our cross section of this transistor, and we know that we have N well here and well over here, and we have the P substrate. Okay, and then over here we have the oxide layer and the gate. Right. The in between of this source and the drain is actually the length, right? The length channel of your transistor. Okay. For the, if I draw it another way, not another way, another transistor with a longer channel like this. This is a gate. And over here we have the length of the channel a little bit wider than the left side. For the short channel, actually the source and drain becoming near to each other because the length is reduced. But for the long channel here on the right side, it is wider in length, meaning the source and the drain is higher, wider, and then it is usually the length is more than 1 micrometer. For the short channel here, usually the length is less than 1 micrometer. Our technology now is shrinking like below than 10, right? 10 nanometer. Okay, so there's some effect on this. One of that is actually the velocity saturation. So velocity saturation is the velocity of the carriers saturates due to collision suffered by the carrier. If you look at on the left side, we have the velocity. This is the velocity graph versus the electric field of the carrier. So as the electric field carrier becomes higher, the velocity of this will become saturated at this side. So it is like almost to the, if you look at here, this one will become some near to, the velocity saturation is near to 10 to the power of 5. And this one becomes a constant velocity.
So this means that when you have short channel or in the current technology, where the transistors are smaller and smaller in nanometer size, there is a limitation to the current because of the constant velocity. So as usually, if you increase the electric field or you increase the voltage between the drain and the source, the current will increase, right? But because of this velocity saturation effect, this means that the current can't go any higher. So it will saturate at that point, right? So you have to know that all these effects that Dr. Arfa is going to talk about today is all the non-ideal effects because of the short channel. And all the transistors now are all short channel because we are going into nanometer technology. Okay, Dr. Arfa, you can continue.
Yeah.
Guys, any question? Are you unclear on any part? You can ask if you want. Anybody? Any question? Do you know everybody is clear on the cross section? Everybody understands the cross section? People are quiet today, this morning. I will start to ask question. Make sure I give you a chance to ask question now.
Madam, can you repeat the last statement?
Which statement? The one said, or my Dr. Arfa's statement, or which statement? The constant velocity.
Madam Anis. Madam Anis statement.
Okay. Okay. Next slide, right? So you look here. So if you see the drain, gate, source, okay, you see the drain and the gate. When you input a voltage there, not the drain and the gate, sorry, drain and the source, you put a voltage at between the drain and the source. You will increase the voltage. That means you increase the electric field. So if you look at the graph, when you increase the electric field, in the beginning of the graph on the left side, it is linear, right? But at some point, it becomes saturated. So that means when you increase, it doesn't increase anymore the velocity of the carriers. This is because the carrier is scattering. That means the carrier is not going in that direction, but it is going everywhere else due to the collisions. Because it is too short and there's too many carriers in one area. So they don't, instead of moving straight, they move all over the place. Maybe like students sometimes, right? We ask them to go one straight line, they go in another place. All right. So this one, it means at some point there will be saturation. Then you can see the graph. After 1.5, it starts to flatten. It doesn't go linear anymore. It starts to go flatten where Dr. Alpha marked in red. So this is the velocity saturation. That means you cannot get an increase in current anymore. All right. And this is the effect of the short channel. You don't get it in a long channel, but the short channel, you get all these effects. Okay. Siapa tadi? Aiman ke? Ke siapa yang tanya
Yes,
tadi?
saya.
Okay, Aiman. Aiman punya apa? Logo ni macam jellyfish kan? Okay, Aiman dah faham dah?
Faham, masih.
Alright. Okay, boleh continue. Orang lain ada soalan? Nak tanya yang sebelum pun boleh.
Because over here, if you look at the equation here, the velocity of the carriers is proportional to the electric field. Means that if you reduce, because your target is to reduce the length, channel length device, right? So the electric field of this carrier will be high. That's why if you look at the graph here, it become as the saturation region here. Due to this, if you reduce the length of the channel of your device. All right. Any other question?
Okay, tak apa. Nanti kita tanya dia kemudian. Boleh teruskan rasanya.
Okay. Okay. So for the voltage current relation of this velocity saturation under linear region, for the short channel device, we know that the voltage of the drain source should be less than and equal to VGS minus VT. All right. And then this is the equation for the current. Right. And then there's a kappa here. And then there's a kappa here. And then there's a VT. And then there's a VGS minus VT. And then this is the equation for the voltage. And then this is the equation for the current. Right. And then there's a kappa here. And then there's a VT. And then there's a VGS minus VT. And then there's a kappa here. And then there's a VT. kappa to the voltage, right? So this is a measure for velocity saturation, 1/1 plus V over electric field of the carrier into length of the channel. So,
So if you see that, the current, the one without the green, all the ones in black is the normal current, linear current equation. Kn dash W over L, VGS minus VT, VDS minus VDS squared. This is normal. This long channel have this. But because this is a short channel, velocity saturation, we add the green term, this kappa and VDS. So what you need to know now that there's an additional term, saturation term in VDS. Okay, like I mentioned, you do not need to memorize this, but you need to know velocity saturation causes what. Okay, I didn't used to cover all this, but apparently when you become a VLSI engineer, they ask you all about these non-ideal effects, and later you will have to take care of them in the layout. So this is why we are explaining where the term comes from. Okay, Dr. Arfa, you can continue.
so for large channel device, usually the kappa here is approaching 1. But if you have it under a short channel device, then the kappa is equal to less than 1. Okay, it should be less than 1, meaning that it can deliver current even in a linear region. Okay, so yeah, like that. So for a saturation region, when VDS is the saturation of the VDS is more and equal to VGS minus VT, the drain current will have this, the saturation drain current will have this equation under the short channel device. We have this kappa into the drain saturation voltage and into the normal equation here, right? Yes, you don't have to memorize, but you just need to know, and then you can just refer back to the notes. So now we have a velocity, still the velocity saturation effect. But if you look at there's two ways to see this. The blue color here is the long channel device, and the red color is the short channel device. If you look at the vertical line here, for the long channel device, this is a normal equation we have, that this thing will be equal to VGS minus VT. But it will, if we reduce the length for the channel device, you will observe that the saturation drain voltage will be lesser, much lesser than the VGS minus VT. So because of this, the device, we say that usually the operation point is in between these two for the short channel device. It should be less than VGS minus VT, and usually it is operating starting from the saturation region here. Okay. So VDS.
So if you can see here, the short channel saturates much earlier than the long channel. So because of this, the short channel current in the device is much less or smaller than the current in the long channel device. For this graph, the left side is IDS, the y-axis is IDS, and the x-axis is VDS. Okay, so just as you know, this is the normal graph, only that if you have the long channel device, the current, you can see IDS can be much higher, but for the short channel device, the IDS is much lower because the channel saturates earlier.
IDS. For long channel, the drain current will be higher than this is a short channel, and the ID is lower, less than that. Okay, so ID set has a linear dependency with respect to VGS. We know that this is a VGS, right? Oh, sorry. VGS, and this is a VGS. So a reduced amount of current is delivered for a given control voltage. Okay. Still for the short channel device, the IV plot for this NMOS. If you look at this is the drain current versus VGS. Okay. If we go back to our, this is what they mentioned. The drain current is linearly dependent with respect to VGS. So if you have 2.5 volt here, the ID will be much higher than if we reduce the VGS value. Okay, so that's why it is a linearly with respect to the VGS. The current, the drain current on the left side here will be proportional to this. Okay.
IDS is dependent on VGS. Okay.
Right. But for Pmos, it will have a reverse way. Okay, so this is linear dependency. Where is the Pmos?
Bawah lagi.
Oh, okay.
Next slide. Okay.
All right, for the Pmos here, all polarities of all voltages and the currents are reversed. If you look at here, the VGS, the drain current will be in a negative side, and including the VGS will be in a negative side. And as we increase the drain voltage, we will have the what we call here the VGS also increase, and we will see also that the drain current will be increased, but yeah, in a negative side for Pmos. Okay, we return back to our last slide. This one. This is the MOS ID versus VGS characteristic. So there's two ways. The long channel. Long channel, usually we will observe the trend is quadratic form for the long channel. But for this short channel, it will be like a linear graph. And it depends on this of ID versus VGS in saturation region. So before this, it will have a zero VGS. But this is the ID condition. If we have the non-ID condition, it will becomes another way. In another way, if we turn off the transistor, we didn't supply any gate voltage at the gate, and then we are expecting that the transistor is turned off. But in a real case, somehow under the short channel device, it will not appear like that. So we need to do something in order to have this overcome this thing, right? So velocity saturation causes the short channel device to saturate at substantially smaller values of the drain source voltage, and resulting in substantial drop in current drive.
Okay, so just in case anybody is not clear, this graph is ID versus VGS. If you go up one slide, Dr. Arfa.
This one?
Up. No, sorry, back.
Right.
Back some more. Yeah, so this is ID versus VDS. And the next graph is ID versus VGS. This is ID versus VGS. So you have to remember, this is the gate. So like Dr. Arfan mentioned, this is the gate voltage. And if you remember, you need to apply a certain voltage to the gate before the channel turns on. So as soon as the channel turns on, there will be current. And as you can see, the long channel produces higher current compared to the short channel devices. So the short channel devices produce linear current, linear with respect to VGS, and the long channel produces current which is quadratic. If you remember the current, can you go back to the current equation, Dr. Alpha?
Current.
I think there was some, go back. Is there a current equation? IDS equals to VGS minus, this one. If you can see here, this current in saturation IDS equals to Kn W over L VGS minus VDT, VDS and VDS saturation. So this is the current equation, right? And you can see here, this is what we are talking about. When you have VGS minus VT, that is the saturation current. And this is when you need to turn on the device, right? It is supposed to, as you can see, this equation is quadratic, right? It's supposed to act quadratic. But when you have velocity saturation, it acts like a linear. You can go back to that graph just now, the blue and the red. This one, right? So this one is short channel. Because of the short channel, it becomes linear. And the long channel becomes quadratic, like normal. Okay, all right. So now, before we go to the next effect, I want you guys to put in the chat box one thing you understood about the short channel effect. Can we have everyone write down? I just want to see whether everybody understood anything or not. Quickly. Wait, let me open the chat box. Everyone write something. What do you understand from short channel device? What is short channel? What is channel? What is the short channel effect? Name one of the short channel effect. Hello, everyone.
Are you guys okay?
If not, I will ask one by one. Quickly write something.
Maybe they're thinking of something.
Okay, short channel effect. Much voltage, current got lost. Yes, we lose current. That's correct, Aiman. The current is reduced because of the short channel. In the long channel, you have larger current. Okay, anybody else? Okay, Ikmal. Short channel effect occurs earlier than the long channel. Yes, the short channel effect causes the saturation to occur earlier than in long channel. Okay, anybody else? Ada ramai lagi dalam ni. Amira, Azimuddin, Mirza, Anas, Fadil, Nik Aizuddin, Najwa,
Everyone is
Aisyah,
here.
Husna.
Okay, very good, Amira.
3, 4, 5, 6,
The
7,
K
8,
value
9,
is less than
10,
1.
11.
The K value is less than 1 for what? Short channel, right? When the velocity is saturated, the voltage will become constant.
Yes. The current will become constant, not voltage. K value. K value is less than 1. Okay, yes, the one that Dr. Arfa summarized just now. Right.
Then got this short channel effect. Got this.
Okay, lagi. Baru 4 orang lagi. 8 orang ni lagi.
Are you guys okay? Aduh.
Azimuddin. Short channel is channel length below 1 micron. Yes, good. So we hope inshallah you will become VLSI engineers who will be designing short channels, right? And then you will know how to fix because of the short channels. Okay, lagi. Tulis je apa-apa. Madam tak nampak pun. Madam tak nampak pun orang yang menulis ni.
Jangan takut. Short
Okay,
channel
Anas.
test
Sisters tak tulis apa-apa lagi pun, sisters ni.
Sister Amira dah.
Amira seorang. Okay, in the IV graph, the long channel will become quadratic and the short channel will become linear. Yes, good. Small diffusion, yes, I like this, Najwa. Thank you. Small diffusion will have small parasitic capacitance. So you have to remember this when you draw your layout. Okay, you must make sure that the diffusion is small. Try to make your layout as compact as possible. The compact layout is beautiful and very good. Produce very good results. Okay, Mirza, velocity of carrier saturates due to the scattering. Yes. Siapa yang ambil semiconductor device hari tu? Aiman Azimuddin? Siapa? Madam tak ingat dah. Ada kan 2 orang yang ambil semiconductor device. You will be learning about this scattering, carrier saturation, all this in semiconductor device under Dr. Fazlin.
InsyaAllah.
Siapa? Anas Senyap pula dah hari ni. Hari tu dia cakap kan? Hari Selasa.
Ashraf. Mirza Ashraf. Velocity of the carrier saturates due to the
Okay,
scattering.
lagi cepat.
Oh, 5 orang. Ramai. Anas kata 5 orang.
5 orang.
Semiconductor device.
Okay, good. Okay, semua, come on. Oh, 5 orang ambil Okay, bagus. So all this will, when you have the background knowledge of what is occurring physically, then when you want to design the transistors, you will have better idea. So this is good. Okay, wait. Siapa lagi yang tak jawab lagi ni?
Kejap Yang girls ada berapa orang?
Okay, tak apa. Kita continue dulu. Nanti kita tanya dia yang lagi 5 orang ni. Saya akan screenshot ni.
Aisyah and Husna.
Okay, alright. Go ahead. Most current source model.
Okay. Husna, mana Husna?
When the length decrease, the electric field increase and the V also increase. Okay, Aisyah, this is good, but you have to start the other way around. Okay. When you have increased voltage, the electric field will increase, and when you put it in a short channel, which is the small decrease, the length decrease, then you will have velocity saturation. Okay, Aisyah? So start daripada V dulu. You apply V, then baru electric field. Baru jadi electric field. Okay, Fadil. The V and I for short channel in Pmos is reversed due to the negative value. Yes, good. You flip, when you want to do the Pmos, you flip it down to the negative side.
Okay, ada lagi seorang sini.
Siapa lagi seorang yang tak tu?
Husna, are you okay?
Menyesal dia masuk kelas tak ramai orang
Boleh. Okay.
So sekarang ni diorang kata kita kena bukan saja mengajar, kena memantau, tengok student kita semua okey ke tak, tidur ke tak, faham ke tak, kan?
Kena ada fokus ni.
Kena ada mentoring. Jadi sekarang ni cikgu-cikgu sangat ni lah kena tahu. InsyaAllah kalau nanti dah buka, nanti kita boleh jumpa ni. How many of you guys are applying to go back to the campus?
I think all because
All
FIP,
final year semua FIP dah ambil FIP. Semua ambil FIP ke?
I think
Yes, madam.
Already on campus? Wah, Najwa ada kat campus dah. Siapa lagi kat campus?
the first batch Wow.
Bukan masuk April ke? Macam mana Najwa boleh sampai cepat sangat?
April, I think the first year. Kan?
Tak.
Tak juga. Maybe
Tak balik cuti. Sian Najwa. Makan okey ke tak tu kat sana? Tak boleh keluar?
Kesian. Yes, cannot. Fellow needs to accompany them.
Dr. Arfa is fellow. Tapi Najwa duduk sama ni. Awak duduk Asia
Sudah.
Hidup je lagi madam. Sian Najwa. Hidup je.
InsyaAllah. Alhamdulillah. Okay.
Okay, kita bagi balik kat ni. Siapa nanti madam cari ni. So kenal lah. Kenal Madam Arfah lah. Ni fellow.
I think majority of them taken with me electric circuit during their year. Kan dah besar dah.
Dah final year dah.
Sekejap je.
Okay. Sambung. Nanti ada lagi setengah jam je.
So I forgot to mention about the effect of velocity saturation for Pmos, because we know that for Pmos the mobility is quite small from the equation of the ratio of mobility of NMOS to the mobility of the Pmos. Usually we have two here, so mobility of P is usually half of the mobility of the NMOS. So due to this, we know that it is half of the mobility of NMOS, right? So the hole usually moves slower than the for the NMOS. So the effect of velocity saturation are less pronounced for the Pmos than the NMOS. So because Pmos has lower and smaller mobility of the holes of this. Okay.
So Pmos tu memang dah lembab, so tak apalah kan. Okay, boleh continue.
Alright. Still remember what is what we resemble this, the current source model. Under what region? We have this transistor equal to this.
Cepat jawab. Madam ajar dah hari Selasa. Cepat, siapa nak jawab? Ni in which region? There are 3 operating regions in the MOS, which are linear, cut-off and saturation. So the current source model is for which region? Siapa yang tak jawab tadi lagi? Semua dah jawab yang tadi. Husna
Husna dah? Belum.
Cepat tengok balik nota. Current source model ni in which region? You only have 3 choice.
This is a repetition question from Prof. Anis.
Saturation.
Yes, good job. Madam baru nak sedih dah, tak ada orang.
Okay, alright. If you look at the first condition is actually not the saturation region when the drain current is equal to 0. So what type of region is this? Sudah, yang balik. Yeah, the second one, yes, I know that this is a saturation region. Okay. The first one?
Cepat. VGS.
I cannot
ID is cut off. Yes,
cut off.
Good job.
Okay, very good. So for the second one here, the under saturation region, we know that for short channel we have this. Okay, for VGS minus VT should be more and equal to 0, with the minimum voltage should be this. And the V at the gate of the transistor should be VGS minus the threshold voltage. This is determined by the voltages at the 4 terminals, the drain, gate, source, and the bulbs, and the set of 5 device parameters here. Okay, but if you look at the this one, if you look at the Pmos have the all the negative side, right? And the NMOS is the positive. These 5 parameters are crucial for the determination of your the drain current here. Okay. Okay. So there's other concern when we reduce the transistor length, the channel length of your device, then we will have other condition. The first one we already discussed, velocity saturation. Second is the subthreshold conduction, or we know it as a weak inversion. And third, threshold variation. Fourth, the parasitic resistance, and last, the latch up. So for the subthreshold conduction is where the transistor already partially conducting for voltage below VT. Maybe if we draw something, then we will see this. And then the threshold variation is when, if you have the long channel device, the threshold is a function of the length for low drain source voltage. But for the short channel device, there is a drain induced threshold barrier lowering. And there's some other effect. We call it this drain induced threshold barrier lowering, or dBL. And the upper end of the VDS range for small l. And then we have the parasitic resistance, where resistance associated with the source and drain contacts here. And the last one is the latch up. Okay. For the threshold voltage, it is given by this VT equal to the threshold voltage at the source bulb equal to 0. And mostly for this one is a function of the manufacturing process, depends on the process of the manufacturer. And the different in work function between gate and substrate material, maybe you can look at this oxide thickness, ferrite voltage, charge of impurities trapped at the surface, dosage of implanted ions. So it depends on this manufacturing process condition. And the source bulb voltage here, this is a soft bulb voltage. Okay, and then this is the ferrite potential, the theta, the theta F here, and this is equal to this under short channel, and it also depends on the thermal or temperature, and the Na here is the accepted ion concentration, and Ni here is at 300 Kelvin of the temperature. We have the 1.5 into 10 to the power of 10 centimeter square. So intrinsic carrier concentration, this is under a pure silicon. Okay, for the last one, which is a body effect coefficient here, it is equal to this value. It impacts of the change in VSB, the source bulb voltage, at the epsilon of the silicon, which is equal to this. The permittivity of this, and it depends on also on this gate oxide capacitance, which is usually equal to this if we use the gate oxide or silicon dioxide. So here.
Okay, so if you look at the threshold voltage, you look at all the terms there. You do not need to be scared of the terms. So let's look at the first one, VTO, which is the threshold voltage. And is VSB, V source bulb. Okay, now Dr. Arfa, can you go to the cross section of the device? Can you go back a few slides? So right now we are supposed to remember two terms, VTO, which is the threshold at 0, and VSB, right, the source bulb. Okay, here. All right, so let's look here. Where is the bulk? Anybody wants to tell me where is the bulk here? Where is the bulk here? Is it in the N plus region, the P-type body, or the gate?
Which one?
P-type body.
Yes, great. Siapa jawab tu tadi? Azimudin.
Azimudin.
Wah, bagus, bagus. Alright.
InsyaAllah. That's good.
So this is the VSB. I asked you to remember the VSB, right? The V source bulb. So that means this is the body. You have to ground it. So when you forget to put the ground. Sometimes you do that in the layout. So then your bulb will not be 0. Your bulb will be floating. You do not know what is the voltage. That is the gate. And can you the bulb is in the middle of the ni.
Yeah.
Tu. That
Usually
one has
we ground both.
you have to ground both of them. Okay, so now we go back to the threshold equation.
Okay.
So the threshold equation, so you see VTO. VTO is the threshold voltage at source bulb 0. So you must ground the source bulb, and this is when you measure the voltage there. What is the threshold voltage? What is the threshold voltage? Means what's the voltage you turn on the channel when your source bulb is 0. Okay, so that's VTO. Gamma just now is the body effect coefficient. Body effect coefficient is the coefficient when you don't put the source bulb to 0, you will have to find out what is the effect. So the engineers put that as a coefficient named gamma, and gamma is a proportion to Q is a constant, epsilon is permittivity, and A is the acceptor concentration. So you have the concentration, how many carriers is in the bulb right now. So then if your your body is doped at a high concentration, the higher the number of carriers in there, the higher the body effect coefficient gamma. Okay, what else? Then you have phi. Phi is the Fermi potential. Fermi potential is a function of T, temperature. It's a function of A, and A again, the concentration. And I is the concentration of the intrinsic carrier. What is the difference between intrinsic and doped? Anybody? What is intrinsic? Intrinsic silicon. What is the difference between intrinsic silicon, P-type silicon, N-type silicon? Anybody?
Intrinsic pure material, while extrinsic has impurities.
Yes, good job Azimudin.
Wow.
Mesti belajar semiconductor device
Hmm.
Oh, kembang hati
Yeah.
Dr. Fazlin. Oh,
MashaAllah.
very good,
Very good.
mashallah. All right. Okay, so I explained all the terms there, right? Phi, SB is the source bulb voltage. Phi, then that's phi again. Okay. All right, next slide.
Okay. This one, Prof. Ani, sorry. This one, quadratic region and linear region is actually they put it this way, or there's some.
This is actually sub-threshold conductance. I think, actually that part maybe should be flipped, but the most important part actually is on the left, below the green line. This is the sub-threshold region. So it means the transistor is not supposed to turn on, but it turns on and it has current. So this is sub-threshold exponential region. Okay, so it has your leakage current, and we do not like leakage current because, anybody wants to guess why we don't like leakage current? The transistor is supposed to be off, but the transistor has current. What happens? Anybody wants to try? The answer is in the slide.
Yeah, in this slide. Current roll off slope.
Not that one.
Mm.
Quickly, anybody wants to try? Tidur semua ni.
Tadi orang tengah fikir. InsyaAllah.
Kenapa? Why we don't want? So let's say, yes, Anas, good job. Increase power consumption. It will drain away your battery. Okay? So later you are going to learn how to make low power circuits, how to make sure the one that is off will be actually off and do not consume any power and do not have any current. Alright, continue. Dr. Parfa.
So for the sub-threshold conductance, I believe this one is a log scale, right? The drain current versus the VGS. That's why we have like this. This is the slope over here, slope. And this is a I off, right? I off. And to turn on this one, there's some, maybe the turn on current is at this part. Just a maybe. Okay. And in order to have this, let's say we have, actually this slope here is the sub-threshold slope. The slope here is the sub-threshold slope. And if let's say the current turn on is equal to maybe 10 to the power of -3. So we exclude first. And the turn off current here is equal to 10 to the power of -9. Then the ratio of this I on to I off is equal to maybe 10 to the of -3 and 10 of -6. We have 10 to the 6. We actually want this one becomes higher, a very large value, so that we have the slope of sub-threshold conductance like this. Okay, and we want it to have the current, the offset, the off current here to be reduced down here as possible, so that we can make it larger value of the value here, right? So due to this, because there's over here we have the slope, the sub-threshold slope of equal to n kt over q ln of the 10. And typically this value is equal to 60 to 100 millivolt. There's another equation for the sub-threshold slope. I think it is also in the textbook. 60 into 1 plus CD over COS. And we actually want to have this sub-threshold slope to be steeper as possible. Steep. Why steeper? Because we want this one to have like a very steep, so that we can lower the current, the off current here, I off. If this one is reduced, then we can make it this one larger, right? So for this one, the minimum we can have is actually the sub-threshold slope here is equal to 60 millivolt per decade. 60 millivolt per decade, because when this one is reduced, or we make it as a 0 here, then we will have the 60 millivolt per decade. But that one is impossible, just for ideal case. And what we have to do is we going to reduce this CD, or we can increase the outside capacitance that we already went through from our first slide. Okay, so we try to adjust this so that we get the steeper of the sub-threshold slope here. right? So it has repercussion in dynamic circuit and for power consumption because of this equation. All right. I think that one is just for the subthreshold. This one, another equation for subthreshold ID versus the VGS. This one also the ID versus VGS, right? In a log scale. So this is from 0 to 0.5 VDS. This is a VDS. If you look at here, this is the I offset, the off current. And then, yes, it is a submicron, so we cannot actually see very clearly, but we can increase this. But based on how to do that, we can control using another equation here, ID equal to this, and then try to maintain, try to reduce a value so that you get the ID also reduced. Okay, this one is the ID versus VDS from 0 to 0.3. And it is controlled by this equation also. And you can look at the what we call it, as the VGS here increase, the drain current also increasing, linearly increase. Right. For the threshold variation, do they put it here? Yeah, the third one. This is second done. So the threshold variation here. Okay. If you increase the length of your device, you will have long channel, right? And you will have a constant threshold variation. But as you reduce the length of your device, the length channel of your device, this one will exponentially reduce. What is reduced? The threshold voltage. So threshold is actually varies as a function of the length of the transistor for low drain source voltage. And if you look at on your right side, the threshold voltage for the lowest VDS or the drain source voltage, you will have the highest threshold voltage. So for the short channel device, the threshold varies as a function of VDS. Or we can call this as the drain induced barrier lowering. There's another terms of this. If you see the cross section of your transistor, and under normal condition, you have the depletion region at the source and drain, and then you have the oxide layer and the gate. Okay, so this is a depletion region, but for under the drain induced barrier lowering, what is this about? Usually we want to supply the VDS, right? The VDS, we want to increase this one. But if you supply more than the higher value of the VDS, not the normal one, the source, you know that it is connected to the source, to the ground. And yeah, for the gate, you keep as it is, you don't apply any voltage yet. But when you increase this one, the VDS on the right side here, and you will tend to increase the depletion region here. Okay, you will extend more the value of here. Why? Because you know that this is a N wheel, right? And this is the P substrate. You have the PN junction here. It will not let you to flow. The current will not flow through here, but it will increase the depletion region But because of the length of this in between source and drain is small, such that when the VDS is getting higher and higher, then the depletion region of the drain side here will be having, we will expand until here. So you will observe like a channel here for both source to drain. And you know that it's supposed to have no, or the transistor should be turned off over here because of we don't apply any voltage at the gate, right? So when this is off, it's supposed not to have any channel in between source and drain. But due to this some drain induced barrier lowering, because of the VDS keep on increasing, you will have some channel here. And then what is drain induced barrier lowering? It is actually, if you observe it in terms of what we call it, the energy band. The energy band, that one susah sikit nak explain. Tapi,
tak payah explain kot, nanti confused.
Confused.
Until ni je.
Okay.
I think you just explain the graph. Go back to the graph there. So if you can see here, as Dr. Alpha already explained, because you already have the short channel and the depletion region is getting closer and closer to each other. So here, it is very easy to create the channel. As soon as you put a small voltage there, the channel is on. But when you put in higher and higher VDS, the threshold voltage will become much lower. So that means, what is threshold voltage? Threshold voltage is the minimum voltage to turn on the channel, right? So this means that at higher VDS, you need lower, it will have lower threshold voltage because of the already made depletion region. So the depletion region at the N well, N plus and N plus will help to lower the threshold voltage. Okay. All right. Last slide. I think it's almost time.
All right. So if you observe on the left side here, the drain current versus VGS, as you increase the VDS, you will increase the drain current, right? From blue to the green color. So drain induced barrier lowering is actually a phenomenon or the effect of the short channel device in MOSFET. And it is referring to originally to a reduction of threshold voltage of the transistor at higher drain voltage. So due to that VDS, as we keep on increasing this, the drain current will be high. So for high VDS, the drain depletion region interacts with the source near the channel surface, lowering the source potential barrier. And the source then injects carrier into the channel without the gate playing role. So the debel is enhanced at higher VDS and shorter in length. This one I think relates to the VDS. The VDS divided by length. The electric field, electric carrier, right? Okay. Right.
Okay, so we finished today's slide. Any questions?
I think it's quite confusing to explain in terms of only a graph and sentence. Maybe if they go through the cross section of what happened when we inject the VDS, you can see what is actually the drain induced barrier lowering. Okay. Any question?
Everybody okay with drain induced barrier lowering? So the important thing that you know will need to revisit. Okay. So the only important thing that you need to know is that at higher for the short channels, the threshold voltage is lower at the higher voltages. Dr. Alpha, can we go at that slide just now? back one more slide at the summary slide just now.
This one?
No, the one that you were ticking just now.
Oh, okay.
This one. Okay, so we done threshold voltage. So the next part is the parasitic resistance and the latch up. Okay. If you have any questions, you can ask later. Okay, so like in the previous class, I think I want you guys to put in what is the most interesting part of the class in the telegram so that you guys can remember one sentence or a few words. Okay, can everybody do that? And then I think we can end the class so that they have time for the next class. Dr. Arfa.
Oh, okay. Right. I think with that we end our class with Tasbih Kafarah and Surat Al-As.
Right. Okay. Make sure you have you put in the few words in the telegram. Cut off. Kat sini.
No, this is, I think the cut off.
Ini yang lama punya. Okay. Okay. Alright. Okay. So we end the class and insyaAllah I see you guys on Thursday. Cepat tulis dekat telegram. Okay.
Let me check the telegram.
So next week nanti kita ada quiz kan? Okay, quiz pakai quizzes. Just short questions. So you can answer. Hopefully nobody will copy, right?
Amira, what is that parasitic capacitance?
Is the unwanted capacitance need to be reduced? Yes,
Or
great.
anyone can help Amira? What is that to parasitic capacitance?
No, but she wrote that already, right? Parasitic capacitance is the unwanted capacitance and need to be reduced. Yes, this is true. This is good.
Okay. Anyone?
So if you are curious on how to look at the transistors, you can follow that Instagram, the one I show you. So this guy always cuts open chips, so you can and show you the microscope pictures. So usually I will bring the students to my lab and look at the layout, the fabricated chips. But since we cannot go to the lab, so I give you the Instagram.
Under my microscope?
Yeah, under microscope.
Wow, mashallah. I mean, previous you.
Yeah, we have the microscope, right? And I have my students, my previous student, master student, Aliza punya chip, Iksan punya chip. Yeah, I still have them, a bit moldy, but they are still in the lab. So you can look at it. Usually I let my students look at it. So, but anyway, we will see. Maybe in April, you guys can, the lab is still there. So we can go, inshallah.
Very good.
All right, everyone. I think we end here because there's only 3 more minutes. Don't forget, I will check in Telegram. All right. Okay. Assalamualaikum, everyone.
Okay. Waalaikumsalam.
Waalaikumsalam. Thank you, madam.
Okay.
Let me off record.
Thank you, madam.